Hi, I'm John Janowick. I'm the Executive Director of the Electrical and Computer Engineering Department Heads Association, and welcome to the Industry Spotlight Sessions. Today's topic and presentation is Tom Lee. Tom is the Chief Education Officer of Quanser. Tom?
Thank you. Very good and early morning to everyone, and thank you very much for inviting me to speak. And today I'm hoping to start a little bit of fun, and what could be more fun than engineering theory, right? My name is Tom Lee, and yes, I have a full-time job at Quanser. I also have a couple of affiliations, one in Canada and the US. I work on interesting education projects with faculty members, and it also impresses the heck out of my mother. So today's topic really is, I think, a common theme that has run through pretty much every discussion that I've seen at this conference, and that's how do you reconcile the traditions of engineering with all the great stuff that all of us want to do. For us at Quanser, a lot of it comes down to how we as engineers develop our own products, and I'll talk about our products a little bit more later. But everybody's either seen or even drawn diagrams like this yourself, some type of an engineering cycle that goes from fundamental concepts right into implementation and all sorts of other good stuff. And historically, the universities have been really good at this kind of stuff, right? The math, the science, more recently some more simulation and computing oriented things. You talk to people in industry, and in fact yesterday during the industry session this came up over and over again. There's a whole bunch of complementary, if not professional, skills that go along with it. You talk to your average kid entering college these days, they're all about this top part. You know, what can you do with it? Can I make real money with it? Is it going to impress my friends and family? All of that kind of thing. And really the educational question these days in my mind is how do we reconcile all of this stuff? And again, over and over again at these types of conferences, people have been talking about this. Now, there's a bit of good news. It's actually not the same as when I was an undergraduate in the 80s. There's actually a lot of activity going on and a lot of investment for all the right reasons. So whether it's just general awareness or TV or what we are doing with teachers to help them understand engineering better, and certainly the whole scene of the robotic competitions. I have a lot of activities that I do with First Robotics and Lego League, and they're spectacular successes in many senses of the word, and we're making really good progress. For us at Quanser, though, especially in that last one of the robotics competitions, we face a fundamental issue, and that's really what today's talk is about. So the actual engineering technique that is reflected by those robotic competitions is broadly embedded systems and control. So very famous systems like Lego Mindstorms or Arduino or Digilent products, meaning the little computer boards, all sort of feed into the basic question of how do you make this gizmo move and sing and dance in an interesting way? And that's, of course, very important. Our company, though, asks the flip side question. And in some sense, for this group, it might actually be a more important question, and that's this. How do you design this thing? Okay, so this thing, in some sense, is the big brother of these fun little devices, but this is, of course, a real-world engineering system. So it's not just space rovers, it's real automobiles, it's real any type of a real-world system. And is the actual motivational benefit of these fun activities enough to really engage the minds and develop the skills that they need to deal with modern complexity? So with that as a preamble, let me introduce our company. We make these wonderful little boxes. We produce the most widely adopted DC servo motor for undergraduate control systems labs and a fair bit of research equipment as well. It all started with this thing called the SRV02 DC servo motor, and over time, roughly about 20 years, we developed an entire portfolio of teaching-oriented control systems plants. And in parallel, we have done a fair bit of work in developing devices for research, for a wide range of critical application areas. So in fact, this is the company today, if not maybe yesterday. It is a company with very respected devices for control systems, for systems that have fairly complex dynamics. Really what I want to talk about today is where we're going next. So Quanser 2.0 as a concept for us is moving from a set of very respected, well-adopted technology, these devices, to really making an attempt at taking our experiences and our reputation to handle more ambitious challenges in education and research. In some sense, I look at this complex issue in 3 buckets: motivation, rigor, and synthesis. And those 3 essential steps have to come together in order to have certainly complete learning, or actually have a complete sense of how you deal with all of a complex engineering process. So motivation for me actually is about magic. So ironically, we are in this magical area, and it's always, that's what drew me into engineering. Not so much that I loved math or physics or anything like that, but I thought it was magical. People were doing magical things, and people continue to do magical things today, and we can't forget the drawing power of that. But to do things like designing a Mars rover or developing biomedical techniques for new diseases, you absolutely need a strong grasp of the fundamentals, and that was stressed yesterday as well by the industry panelists. And so we need to figure out a way to bridge that. And finally, I'm a big believer in the big picture. I can't remember how frustrating it was as an undergraduate trying to figure out why are we taking these differential equations courses, and nobody ever explained it to me. And it wasn't until I started grad work that all of a sudden one magic day a bell rang in my head and everything made sense at that point. I think we owe it to our students to try to give them that big picture from day one. So how are we going to do it from our own product point of view? So as I mentioned, this is where we started. We are primarily focused, our historical business, in the junior year or senior year of the undergraduate program, and also the grad side of things. So the undergraduate control course is our domain, as well as related research areas further on. In many ways, we're now focusing on obvious educational contexts that relate to that control program. Great thing about control systems is it's naturally interdisciplinary, and it pulls in all sorts of very important topics that students face in their undergrad program. So it has a huge potential for helping create that big picture clear, make that big picture clear for the students. So I'll talk a little bit about this, but definitely going into the senior year, a lot more focus on design projects and capstone projects, that sort of thing. Going down the ladder into some of the more fundamental science courses, and even in first year to actually get some of the key techniques that one might see today in the senior year appropriately implemented at the freshman level. And we also dare to dream that one day we can start tackling some of the issues in the bridge to K-12 and also industry. Now, with industry, we actually already have a fair bit of industrial activity, so we're not too concerned about that, but that K-12 is another zinger that we need to deal with. When we do our new projects for this Quanser 2.0 concept, we look at some fundamental dimensions. One is very important for us, real engineering workflow, especially in the area of control, where there is such a disconnect between the standard textbook and what control engineers do in the real world today. And it's not like the real world control engineers are doing sort of easy, just sort of cobbled together stuff. They are actually doing very ambitious, rigorous work themselves, but the two aren't connecting right now. So we look at what kind of things people really do and try to abstract that in an undergrad-friendly way. Again, it's naturally interdisciplinary, the kind of work that we do, so all sorts of very interesting application areas, the rigor and practical harmonized. And finally, just the whole notion of taking advantage of modern digital platforms for information. So whether it's network technology, mobile technology, different digital media types, all of that is coming in, and we have really interesting projects for all of that. And we're doing all of this because of this basic reality. So this is what all of us did, 20 or so years ago, and that was control engineering, and it's no wonder we face this situation where so many students are just wondering what the heck is going on. So one example of a case study where we took an existing course and adapted it to more modern needs is the University of Toronto, where we took a control course and actually mapped a real application onto a traditional hardware setup. So this is a traditional lab setup. DC servo motor, you have some sort of a control software, and you do a bunch of interesting things with reference signals. It's not bad, and that's in fact how we earned our money over the past little while. But what we did more recently is we added a second motor and actually added some models from a real application area. Then we spiced it up with some more modern software from National Instruments, as well as some little mojo on the graphical side, and also added a little gaming element, and this is what you got. So here's a brief video of it. We call it the Quanser driving simulator, for the lack of a better name. And you can see it actually looks like a real video game. And for the most part, in a first lab, students, they are very comfortable with this. They're going through their driving. It's sort of this cool virtual reality style visualization. And this is actually lab view. You can funk it up with all sorts of cool interfaces. So the engineering data is now flowing out through this type of interface. But underneath it are real DC servo motors, and there is a full hardware-in-the-loop connection between the devices and the control concept. So the key takeaways from that, it's familiar and fun, which raises the motivation, but it still retains the theoretical foundation. It's a real industry-oriented hardware-in-the-loop system. Importantly, it's also a showcase lab, meaning if you have demos to give incoming students or people with money, all of that it shows really well. We have a demo at this conference, and the method is very compatible with most Quanser systems. So very briefly, I want to talk about first-year computing. This is the other area that we're looking at. How do you go from the old stinky C course to something that inspires people? You don't do it with Hello World. And what we're doing is taking the engineering view of computing. The computer for engineers is a combination of a toolkit, a prediction tool, and something to control things. That is not a worldview that the typical high school student is familiar with. So we are taking what is realistically engineering from a computing point of view and rebuilding a course. One of our partners is the University of New Mexico. One portion of a very larger project we're doing with them, we are working with them to rewrite the first-year computing course. Now, I'm not going to obviously go into details, but suffice it to say, we're moving away from the algorithmic-centric view of first-year computing that has always existed to an engineering data-centric viewpoint. And we're hoping that within about a year's time, we'll make some real progress in that. Finally, this is a personal mission of mine. I've only been with Quanser for 2 years. Prior to that, I worked for 20 years for a math software company called MapleSoft, makers of the symbolic computation product. It is my life mission to make math make more sense to engineers. So I have started formulating some concepts. I have found some willing academic partners. I don't have a lot of details to share with you, but I fundamentally believe that the technology and the tool chain is there now. The concepts and the motivation is there, but ultimately that elephant in the room where every time you bring a topic up, the profs say, why don't we leave that discussion for another day? It's sort of complicated at our institution with factoring in who teaches math and what we have. So it is a holy grail for us, and we look forward to talking to many more professors to work this out. So to conclude, it's all about this, of course, and our goal as a company is to really provide a positive influence and a contribution to reconcile all of these disparate elements. Thank you.